Swayam Prabha. Digital India. Educated India.
In case of minimization problem, the overall objective function value is going to increase. In case of a maximization problem, the overall objective function value is going to decrease. So to ensure that we get an optimum value, this particular constraint must be 0. This particular function, we will find that it is actually applicable for the equality constraint, as I said, and the extent, to what extent it is going to be added or subtracted from the objective function depending on the problem maximization or minimization problem will depend on the penalty parameter we are going to use. And in a general case, in every iteration it is going to be increased from a small start value. And if you see that if we have a feasible solution, then no matter what is the penalty parameter value, which again, let me go back to the equation. This was my penalty parameter value. No matter whatever this value is, how high value this value is, if my obtained solution is feasible, then this is going to be 0. So it won't have any effect. But if it violates, then immediately it is either going to increase the objective function value or it is going to reduce the objective function value in this case. So we may not get the optimum solution. And if you see that the way the penalty function is operating, it is effective only in case of the infeasible points. It is not going to have any effect if the solution is feasible. So in this case, if the penalty is applicable for the infeasible point, we call it as exterior penalty term. So this is the only function we have for the equality constraint. The other functions we are going to discuss are related to the inequality constraint. One such function is infinite barrier penalty function. This infinite barrier penalty function works in such a way that whenever a particular solution violates the inequality constraint, then we estimate the penalty function as this. This will give certain value. If it does not violate, then this function is going to give us 0. So it is very clear, like in case of inequality constraint, if we have an inequality constraint which looks like this, so any point which is on this side is going to violate, we are going to have a value for that, and it depends on this value. If it violates to a higher extent, this penalty is going to be high. If it violates by a little bit of amount, suppose the point is very close to the boundary, then this value is going to be low. But if we get a point on this side which is actually in the feasible region, so this particular constraint is not going to be violated, and in that case we are saying this value is going to be 0. So it won't have any effect on the objective function. As I said, it is applicable for the inequality constraint, and the penalty parameter in this case is considered a large number and for one sequence only. So if you are using the infinite barrier penalty, we do not need to change the penalty parameter in every sequence or every iteration. So in that case, the objective function value or objective function is going to remain. And if you look into carefully, only the infeasible parameters or infeasible solutions are going to be penalized. So again, this is for the exterior penalty. Another type of inequality penalty function is known as log penalty. So in log penalty, we simply represent the constraint function in this form, and as I said, it is applicable for the inequality constraint. If you look into this particular function, it cannot assign penalty to infeasible solution. If it is infeasible solution, this value is going to be negative. If you recall, we said in our base function gjx is less than 0. So whatever solution we are going to obtain, this value, if it is feasible, it is going to be negative, and already we have a negative sign, so eventually we'll get a positive value inside the ln, and we can get a value for that. However, if we find that the solution is infeasible, then this value is going to be positive, and if we try to replace it in this function, we are going to have a log of negative value, so which we cannot solve. So for this reason, this particular function is applicable for the feasible solutions only, and in that case we are saying it as an interior penalty term. And again, if you see, you'll find that the penalty is going to be very high when the solution is close to the constraint boundary. So if this value is very less, which means it is very close to 0, then this penalty, when we do the natural logarithm, we'll find the value is very high. But if the value is high, then the penalty is going to be low. It helps when we want the solution not very close to the boundary, rather we want the solution to be off the boundary or far off the boundary. So any solution which is coming very close to the boundary is again going to be pushed towards away from the boundary. However, this particular solution or this particular method does not take care of the infeasible region, so we have to separately take care of that while solving. For an instance, the start point which we want to use in the solution should be within the feasible solution rather than in the infeasible solution, and in this case the penalty parameter which we use is sequentially reduced from a very large number. So every iteration the objective function is going to change as the penalty parameter is going to change. Another type of inequality constraint penalty function is the inverse penalty, which is represented as this. It is also applicable, as I said, for the inequality constraint, and this function also cannot assign penalty to the infeasible solutions. It can only do it for the feasible solution, and for that reason we are saying it as a interior penalty term, and this is useful for the boundary points. So if it is close to the boundary points, that means we are going to get a higher negative value, and if we are adding that the higher negative value with the objective function, it is further going to lower the overall objective function in case if we are minimizing the overall objective function. So let me go back. If our solution is very close to the boundary, then this value is going to be low, and if this is low, overall this value is going to be high and with a negative value, and if it is a negative value, let me go back. Here you will find that if it is a negative value, the objective function is further going to be reduced, which means that is the preferred answer in case of the minimization problem, which means we are looking for solution which is close to the boundary of the constraints. And in case of maximization problem, the negative value with the negative is going to be positive, so it is going to add or increase the objective function value, which means it is better than the point which is away from the boundary. So in a nutshell, this particular function helps to bring the optimum solution closer to the constraint boundary, whereas this particular function pushes the optimum solution away from the boundary. There is another inequality constraint function. It is known as bracket operator penalty function, and this is represented as the square of the constraint when it violates. If it does not violate, then we say it as 0. And this bracket operator penalty is similar to the equality constraint penalty function which we had discussed at the beginning. However, in the equality constraint, we did not have the condition where we are checking if the constraint had violated or not. In this case, we are checking that if it has violated or not. So again, if I have to draw, if this is my constraint, any point which is inside this, it's not going to violate, and in that case the function value is going to be 0 for the constraint. And if the point is outside here, the point is going to generate a constraint value which is going to be violated and which is going to be squared and added to the objective function. So hence it will further increase or decrease the value significantly depending on whether it is a minimization or maximization problem, which will force the solution to bring this point inside the boundary. So as I said, this point or this solution is applicable for the infeasible points. Hence this is the exterior penalty term, and in this case the penalty parameter is sequentially increased from a small value. So we have to understand which type of penalty function we are going to use, and accordingly we have to choose the penalty parameter, whether it is going to be sequentially increased from a small value or sequentially decreased from a very large value. So let us look into the generic algorithm of this penalty function. In this case, like any other method, in the very first step we have to set the I counter to 0, and then we have to select a start point which is in the feasible or infeasible depending on the problem which we are choosing, and then we have to also select the penalty parameters depending on which penalty function we are choosing or which type of penalty function we are choosing, and then we have to also select a sufficiently small number for the termination criteria and the suitable penalty terms which are or the functions which we want to use. At this point we also have to choose the penalty adjustment factor alpha, which is going to be between 0 and 1 for the penalty terms which are of interior penalty type, and which is this value alpha is going to be greater than 1 if the penalty type are exterior. Then we need to develop the transformed unconstrained objective function like we had shown earlier. Once we develop that, with the help of the starting point which we obtained, we have to find a new point such that the new point is optimum based on the penalty parameters which we have and the penalty terms which we have used. Once we find that optimum point, we compare the transformed objective function value and see if that is less or greater than the termination criteria which we have set. If we find that it is still greater, we need to revise the penalty parameters. In this case, we have to multiply with the alpha value with the previous value for both inequality constraint and equality constraint. We increase the counter by 1 and then go to step 2. So once we go to step 2, since we have adjusted the penalty parameters, we need to redevelop the transformed unconstrained objective function, and the process continues till we see improvements in the transformed objective function value. Once we see there is no improvement or the difference is within the termination criteria, then we basically terminate and report the new obtained point as the optimum solution and the objective function value as the optimum objective function value. Now we'll be looking into this particular method through an example. We are going to use the same example which you have known in the last few class. In this particular problem, we are going to minimize this function. Along with that, we also want to introduce an constraint which is indicated in this. If you recall, we used to have the objective function in the standard form as less equal to or less than 0. In this case, it is greater equal to 0. We also have two other constraints for the design variable x1 and x2, in which both needs to be greater than 0. In this particular problem, we have chosen the bracket operator penalty term for the solution. You can choose any other penalty term for the same problem and see the efficiency of those as well. So we are starting from the point 0, 0. We have set the penalty parameter as 0.1 for the inequality constraint and the alpha as 10 and the precision value as 0.1. Now we do not have any equality constraint, so we do not have the inequality constraint penalty parameter or its associated alpha value. What value we are going to choose will completely depend on the penalty term we are going to select. So once we know all this, we can now form the transformed objective function, which is minimization of this. So this is my main objective function, which is going to be here. Then I have to indicate the constraints. So constraints, we have to multiply with the penalty term and the penalty parameter. So penalty parameter is 0.1 and the penalty term is this in case of bracket operator penalty. And this particular sign means whenever it violates, we'll be using this value, whatever we are going to obtain. If it does not violate, it is going to become 0. We also have the constraint for the each design variable. So the penalty parameter multiplied by the penalty term for this penalty parameter and this. At this point, we started from x0 as 0, 0. We'll find that the original objective function value of x0 is going to be 170. Once we introduce the transformed objective function, we'll find that the objective value of this transformed objective function is going to be this at 0, 0. This is the point. At that point, it's going to be this. If you see this particular problem, it has now become a unconstrained multivariable optimization problem. So we can use the techniques which we have learned in our previous lectures to solve this, and you should choose one of the suitable method to solve this. In this case, we have used the Cauchy's method, and once we use that method, we found the solution. X1 is going to be this particular point. At this particular point, the original objective function value is going to be 5.709, which is quite an improvement over the previous point when we looked into the objective function value at 0, 0. And the transformed objective function value is going to be 26. Here also we do see certain improvement. And then if we look into the changes in the objective function value of the transformed function, then we'll find that the change is still significant compared to the precision which we have set. Since this was our first point, so we did not use the penalty parameter and the penalty term to estimate this component. We have just used the original objective function value. So this completes the first iteration. Before getting into the second iteration, we need to find out the value of the penalty parameter. So we said the multiplication factor alpha is 10, so we are multiplying it with 0.1. Now it becomes 1, and we'll start the next iteration. Once we change the penalty parameter, we need to rewrite the objective function for the transformed objective function, and once we do that, we'll see that we have replaced the penalty parameters in this case. Now this is again unconstrained multivariable optimization problem, which we can use Cauchy method, and if we do so, we'll find the point as this, and the objective function at this particular point is going to be this, and the objective function value of the transformed objective function is going to be this. If you look into the constraint, you will see that it is still violating the constraint, and if we see the changes, we'll see that the changes is significant. Hence we need to further increase the penalty parameter, so we are again multiplying with 10, and now the penalty parameter is going to be this, and we'll start our next iteration. In the next iteration, our transformed objective function is going to be like this, where you will see the penalty parameters are now 10. We use the Cauchy method, which is going to yield the x3 value of this, and if we look into the value of the transformed objective function, it is going to be this. At this point also, you may find that the constraint is still being violated, but the amount of violation is very low, and once we compare these values, we'll find that it is still not meeting the precision, so we do need to continue, and before we continue, we need to increase the value. So earlier it was 10 times 10, it will be 100. Once we make it 100, and we'll start for the next iteration, and the process will move or continue in this way until it reaches the point where we won't see much improvement over the point, and it will satisfy this condition, and at that point we are going to terminate. So this process requires lot of iterations, and in these iterations, sometime in a very complex problem, we do need the help of the computer or computational system, but for the simple problem, it can be hand calculated. I would insist to go through this particular problem using different penalty term and choose suitable penalty parameters and try to solve for at least one or two iteration using one of the unconstrained multivariable optimization techniques or the methods we had discussed in the previous class. So with this, our constrained multivariable optimization solution ends, and in fact with this also we are ending our discussion on the multivariable optimization techniques. In the next class onwards, we'll be moving on to the linear programming problem. Before we go to the next class, I would like to summarize on the methods which we have learned so far. We discussed various numerical methods to solve unconstrained single variable optimization problem. There we had discussed certain methods which will help us to bracket the optimum solution, and then we also discussed certain methods. From this bracket we can actually come closer to the optimum solution. With the understanding of the single variable optimization techniques, at least some of them, we learned some of the numerical methods which can be used to solve multivariable optimization problem. When we looked into such problem, we also saw that there is also need for methods that can manage or that can solve multivariable optimization problem with constraints. So in today's lecture, we saw a few methods which can be employed or used to solve the constraint multivariable optimization problem. In this solution process, you found that we are again using the basic principles or basic understanding of the unconstrained multivariable optimization problem. Whether it is the random search method or whether it is the complex search method, which is equivalent to the simplex search method, or whether it is the penalty function method, where we need to use one of the unconstrained multivariable optimization problem solution techniques after converting the constraint problem into a transformed objective function, which is essentially a unconstrained multivariable optimization problem. So if you look back, all these methods are related, and without understanding one method, we cannot jump to the another method. We do need to have proper understanding, good grip on the method which is used for the single variable optimization problems, which is used for the multivariable optimization problem. Then we can actually solve the constrained multivariable optimization problems. Apart from the methods or the techniques which I have discussed so far, there are also other methods. For example, genetic algorithm is there, ant colony optimization is there, and there are many more such methods. It is difficult to cover, or it is not possible to cover all such methods in a single class or in a course like this. I would recommend that you should further explore and understand more and more methods, and those understanding is going to help you in future whenever you are developing or you are working on some optimization problem and using one of the techniques. When you are solving a real world engineering problem, you will also encounter situation that will lead to relook into the method which you are employing, and which will require you to combine your understanding of various methods and apply it for the efficiency. So when we talk about the efficiency, what is our goal in any of this solution? Our goal is to ensure that we really reach the optimum solution, or if not the optimum solution, closer to the optimum solution. It is so close that it is acceptable for our situation, and when we are reaching there, it is computationally efficient, which means it requires less number of function evaluation and it requires less number of iterations. If you search in the journal papers or many published literature or anywhere, you'll find that the researchers are actually trying to find out the best suitable method or best method for the problem they are trying to solve. And for the same problem, people have used many techniques, changing some of the basic techniques, basic methods, and try to solve the problem which is faster and better than all the previous techniques. With this, I'm going to conclude today's session and also concluding the session on the nonlinear programming. Next class onwards, as I said, we'll be moving into the linear programming methods. Thank you and see you in the next class.